recording. It's recording. Sharing. It's sharing. Okay, good. All right, everybody's here. Let's get going. You can see my shared screen. So this is a little twist on medicinal chemistry, and I think you'll find it interesting, especially if you haven't experienced any of this stuff. Use of chemical informatics tools, which is basically, computational chemistry. But maybe applied to small molecules, and that's something you possibly haven't seen before. I mean, you may have taken a computational chemistry course, but usually that might focus on like big protein or big molecules like proteins and things. So chemical informatics deals with small molecules like drug type molecules, right? What are physicochemical parameters? So these are things that, like a parameter assigned to a drug that may be related to its solubility or its drug-likeness, things like that. Yeah. So anyway, let's get going. So we're gonna first introduce these physicochemical parameters, then we're gonna get into a little bit more into chemical informatics. All right. So there's a really good book that I recommend. I can probably find a excerpt from this. Overall, the book is really good. So if you're into medicinal chemistry and want to, read more, this is definitely like a graduate level or maybe postdoc level type textbook on all sorts of topics related to these pharmacokinetic, physiochemical properties and things like that, and drug likeness, those ideas. It's a pretty cool topic. There's a lot to it, and this is a book where I got a lot of the figures and things related to this. All right. Okay, so these are the things we're going to talk about. Physicochemical properties, review oral drug absorption through the gastrointestinal tract. We'll talk about log P and C log P, which is a kind of a measure of aqueous solubility. Polar surface area, and PSA is polar surface area. TPSA is topological polar surface area, which are another measure of basically polarity of a drug, and that's a big deal when it comes to the drug likeness. And then we're going to talk about something called the Lipinski Rule of 5, which is kind of like an easy guideline for drug likeness, to see, like, is a molecule drug like? What does that mean, drug like? I mean, because we assume most drugs are drug like, right? But what if you're trying to discover a new drug? It'd be really nice if you could easily characterize the structure of a drug as being, drug-like, so that if it's totally not drug-like, you may skip it or move on to something else, right? So it's kind of like something you might do in screening, like high throughput drug screening. You have 100,000 molecules you're assaying to look for a drug, and it'd be nice if you can quickly determine, like, if a molecule is even potentially drug-like, orally absorbable, etc., from the get-go. Anyway, there's two types of this. There's the Lipinski method, the Lipinski Rule of 5. That's pretty standard. There's also something called the Weber rules, and these are we can pretty easily use them, and we will. It'll be fun. Then we'll get into chemical informatics and computational tools. We'll talk about something called SMILES. Has anybody heard of SMILES before? Aside from when you're walking down the street smiling? SMILES. Has anybody ever heard of that? maybe something that you have never heard of. It's a chemical structure method that's text-based, which is pretty cool. We'll also talk about generating 2D and 3D structures of molecules, which you've maybe never done before. Prediction of drug likeness, these Lipinski and Weber criteria, using computer programs and websites. Prediction of metabolism. Can we predict phase 1 and phase 2 metabolites? Because we're done with metabolism. Hopefully you've watched all those videos on phase 1 and phase 2 metabolism now. We're going to briefly talk about virtual screening, which is like using a computer to try to find a drug. That's a pretty cool idea, right? Just using a computer to find new drug molecules, and not, you should validate it with experiment, but if you can do a lot of stuff on a computer, you might as well. In silico synthesis, what does that mean? In silico synthesis, that sounds pretty crazy, because synthesis we think of as a lab technique. Could we actually do synthesis in the computer? Well, we kind of can. We can't actually make the molecules, but we can make libraries of molecules on the computer using kind of virtual synthesis, right? And then we can screen them using virtual screening. It's a pretty cool idea. We'll do it. You'll do it. You will actually be doing in silico synthesis yourself as a homework assignment. Homology modeling, docking, and molecular dynamics. I'll just introduce a couple of these topics. And we have a couple case studies. Modeling of GP41 inhibitors, HIV fusion inhibitors, which is something I've done in my lab. Also, SLC26A3 is one of our channel protein projects, and we've done some computational modeling of that. I actually have a cool case study. We could call it case study number 3. During the pandemic, I created a COVID-19 protease inhibitor from scratch using computers, and we published it. I haven't created PowerPoint slides of it, but I may try to sneak that in too. We did that through docking, computational docking. Me and my buddy were locked at home, so we did a huge project and screened 100,000 molecules on a computer, and then we found somebody to do the real assay, and we discovered new molecules as COVID-19 protease inhibitors. So I may try to sneak that in. Otherwise, I can at least give you guys the paper. It's not the most exciting thing, but it was actually sort of a pandemic project that was fun. Okay, so let's get into physicochemical properties. Oral absorption through the GI tract. Okay, so drug absorption occurs usually in the stomach or small intestine, sometimes the large intestine. Usually, a good oral drug will be absorbed kind of early. Maybe if you want, quick acting drug will be absorbed early. A later acting drug might be absorbed later. But each stage of this process, the pH increases. That's kind of interesting, right? Because we know the stomach's acidic, but your intestines are actually kind of basic or neutral to basic, right? Definitely less acidic. So if you take a drug orally, it enters your stomach, kind of acidic environment, and it sort of transitions into the duodenum and the jejunum and the ileum. The ileum is kind of like the last stage of the small intestine, and the pH kind of increases. So that what effect does that have on a drug? Well, it depends on if the drug is ionic or has a ionizable functional group. Okay. So pH increases as we transition through this process. This shows some of the pH ranges, I guess. Stomach, it depends on if you're fasted or fed. So the pH is a little more intensely acidic if you're fasted, and then it gets a little more basic, I guess, in the fed stage. But it does increase sort of continuously through these stages to slightly basic in the ileum, which is the last stage of the small intestine. Of course, the time into these different spots increases, right? If you take a drug orally, it can be absorbed pretty quickly, which is That's nice for like if you need something to be absorbed kind of quickly, like a painkiller, right? You have a headache, you would like the headache to go away kind of quickly. A lot of the painkillers are absorbed kind of quickly in the stomach, which helps, right? I mentioned I suffer migraines occasionally, and my the drug I take under the tongue, so it's actually very quick. It can be 10 minutes, 15 minutes into my brain, and it actually has the anti-migraine activity. But this is for oral drugs, which generally speaking, people like to use oral drugs or design drugs that are orally available. So drug's protonation state can affect its ability to absorb at these different stages. Anybody know why? Or like, does that mean protonate? What does protonation state mean? Like protonation state. Have you ever heard of that word before? Protonation state? Something about protons? What does that mean? Anybody know? So does anybody know any functional groups that have different protonation states? May have never thought about that, right? But we know of like a carboxylic acid can be protonated, but is it always protonated? I mean, it might be deprotonated, right? So carboxylic acid has a proton, and it's acidic, right? So at physiological pH like 7.4, a carboxylic acid is not protonated, right? It loses the proton because it's acidic. And so we have that thing called the Henderson-Hasselbalch equation, which we'll show in a second to review that. But yeah, and the other thing, do you think ionic molecules or neutral molecules are the best to transition through a membrane, like a membrane in your intestinal membrane? Does that matter? Does that have to be protonated, or I mean, does that have to be ionic or neutral? I mean, anybody know? So are membranes neutral or ionic? Like a lipid bilayer. So usually neutral is greasy, right? So do ions like grease, or do neutral molecules like grease, the greasy environment? So basic point is that neutral molecules are more likely to transition through a membrane, right? A neutral molecule, like maybe a fatty molecule, right? But something that's ionic, like negatively charged or positively charged, is why would that like a greasy environment? You know, it doesn't like that. So that's what we mean by a protonation state. It can affect its ability to absorb at these different stages, especially if the protonation state depends on the pH, right? Right? A carboxylic acid is not protonated at pH 7, or it might be protonated at 1.4 or whatever. Ionic needs transport, somebody sent me, and that's true. There's other ways for ionic substances to be transported, but I mean, or they can just kind of sneak through the cells, I guess, not go through a membrane, but go in between cells. There's other ways that ionic molecules can be absorbed. Okay, but let's think about naproxen first of all. So it's a Aleve. It's a orally available non-steroidal anti-inflammatory drug. That's a painkiller. It's got a pK of 4, right? So we'll say at pH 2, pretend it's pH 2, like in the stomach. Is this protonated or not? For the most part. If it's more acidic than, if the pH is more acidic than 4, then yes, it's mostly going to be protonated, right? What if the pH is 7? Is that going to be protonated, like in the ileum, which is the end of the small intestine? If it's 7, somebody messaged me neutral, and that's not true, right? because pH 7 is more basic than the pKa of the molecule, right? Right. Okay, and what does the pKa mean? Does anybody know, like, okay, say the pH is exactly 4. The pH, say the pH is exactly 4, the pKa is 4. What does that tell you about this functional group? Anybody know? This is stuff that they probably taught in Gen Chem, but it may have been a while that you've thought about it. But what is I mean, at pH 4, is it this, or is it something else, or is it a mixture of things? And somebody said correctly, 50% protonated, right? At the pH 4, a pKa 4 functional group will be 50% protonated, 50% deprotonated. That's right. And that's the Henderson-Hasselbalch equation that we'll see in a second. All right. Yeah. Okay. Good. And fluoxetine, which is the selective serotonin reuptake inhibitor, Prozac. It's got, well, the funny thing about this is fluoxetine doesn't contain 2 protons. It contains 1 proton, right? It's a secondary amine. So this is technically not exactly fluoxetine. It's fluoxetine plus an extra proton, right? If we envision fluoxetine itself with just 1 proton, what's the pKa of that? Anybody know the pKa of an amine? Normal pKa of an amine, like imagine only 1 proton, and then only 1 proton and the pKa of it. Anybody know what amine pKa's are? Big number, small number? Or like ammonia. What's the pKa of ammonia? It's huge. It's very, very, very non-acidic, right? So an amine proton is not very acidic, but when we consider a drug-like molecule, we would consider basically the adding of a proton, and that will tell, based on this number, pKa of 10, we can kind of determine the protonation state, right? So at pH 10, a pKa 10 functional group will also be half protonated, half deprotonated. All right, good. So to quantify the amount of neutral permeable drug at a specific area of the GI tract, we use the Henderson-Hasselbalch equation. So that's a Gen Chem equation that you may have not seen in a while, but it's a nice formulation of this, and we can quickly figure out how much protonated versus how much deprotonated, right? Okay, so for a weak acid, and that's what we're going to call like naproxen up here, a weak acid, we're going to consider its pH equals pKa plus the log, the log base 10 logarithm of A minus divided by HA. So this will tell us the relative amount of A minus to HA, right? Okay, so we'll solve this in a second. We'll try this out. Okay, and for the pKa, of course, is the pH at which 50% is ionized, right? That would apply to either naproxen or fluoxetine. So it's a good thing to remember about pKa values. It's the 50% point. Okay, kind of like an IC50, but for acidity, right? Okay, in a weak base, it's the same equation essentially, but we would do the pKa. It's not the pKa of the drug, it's the pKa of the conjugate acid of the drug, right? So this, what we're showing up here is not fluoxetine, it's the conjugate acid of fluoxetine. So pKa here is a little bit misleading. It's not just the pKa of the proton, you have to imagine an extra proton on there, and then what the pKa of that is, which is 10. The single proton is like 35 because amines are very, very non-acidic. A normal amine is very non-acidic, right? Okay, and then it's going to be the base divided by BH plus, which is the protonated base. And up here you can see BH plus would correspond to this, right? It's the base with an extra proton, and B would be the non-ionized form. Okay, good. Okay, so how does this work again? It's a membrane in the GI tract, like in the small intestine. It requires drugs to be sufficiently lipophilic and normally neutral. So if you envision a lipid, bilipid membrane, a drug, if it's neutral, can kind of just transition through this greasy environment and go from one side to the other. And then there's, of course, there's water molecules that are kind of locked out. There's a polar head group on the lipid, and then a kind of greasy inside part, okay? And this allows passive diffusion of a drug molecule, okay? So it's not absolute. There are ways that polar and ionic drugs can get through, into your body. There's something called the paracellular space, which basically means space between epithelial cells. There's some space. It's not like everything's like a complete wall, right? There's mechanisms for ionic molecules to be absorbed. Okay, it's just maybe not as efficient. All right. Overall, the drug absorption can occur through several places and different ionization states: stomach, duodenum, jejunum, and the ileum. Okay. So we're going to do a little calculation on my page. We're going to calculate the A- divided by HA for fluoxetine. We're going to do it in the stomach in a fasted state at pH roughly 2. We'll also do it in the ileum fasted state at pH roughly around 8-ish or so, okay? So we'll do that. And then we're going to do it for fluoxetine, but it's a base, so we're going to use the different formula. I'll write it out on my page as we do it. And then these are, basically we're going to use these Henderson-Hasselbalch equations. All right, so let's do it. Any questions yet? Hopefully that some zoom, good enough zoom for us. All right, cool. So we'll do naproxen first. I'll draw it kind of large, not perfectly focused. So naproxen in the stomach, which is pH is roughly 2. The equation is pH equals pKa plus logarithm of A- divided by HA, yeah? So 2 equals 4 plus the logarithm. Basically means that it's going to be -2 is equal to the logarithm. And A divided by HA, A minus, that is about 0.01 to 1. So generally speaking, I mean, what does that mean? It's about 1% ionic, 99% neutral. So that should absorb quite well, right, into the stomach, and that's these carboxylic acid drugs are usually absorbed pretty efficiently in the stomach. Now, if we do the same calculation, but in the ileum, kind of the end of the small intestine, fasted state. Top is also fasted state, fasted. So the pH is roughly, we'll say around 8. The equation is pH equals pKa plus log. Also same, A minus HA. Now the pH is 8, pKa is 4, plus log, blah, blah, blah. And so do the math. Eventually, A minus over HA equals about 10,000 to 1, meaning it's about 99.9% ionic and 0.1% neutral. So that's definitely interesting. It's a cool use of this Henderson-Hasselbalch equation. And to just show you, I mean, that certainly in the stomach, it's more efficiently absorbed because the pH in the stomach keeps that molecule protonated, and as protonated molecule, it just absorbs more efficiently. Okay, cool. All right, we'll do the same thing for fluoxetine. Fluoxetine, we'll do it in the stomach first. Fasted. pH is around 2. Now it's pH equals pKa plus the logarithm. Now we use a slightly different formula, which is neutral molecule. BH plus is the protonated molecule. Conjugate base, it's like the base version of the molecule and the conjugate base version of the molecule. Okay, so that's 2 equals 10 plus logarithm, blah, blah, blah. -8 equals the logarithm, blah, blah, blah. And essentially we do 10 to the x, you know, to get rid of the logarithm, and essentially it becomes b divided by bh plus equals 0.1, 2, 3, 4, 5, 6, 7, and then 1 over 1. So this is about like 10 million times more protonated. Fluoxetine's like about 10 million times more protonated in the stomach. So there's very, very few unprotonated versions of the molecule in the stomach. And that just shows, you know, how dramatic this effect is. It's a basic molecule, right? A basic molecule in an acidic environment is just going to be very, very protonated, right? Okay, cool. And then if we do the same calculation, fluoxetine in the stomach, sorry, in the ileum, fasted state, pH around 8, pH equals pKa plus logarithm, blah, blah, blah. Now 8 equals 10 plus logarithm, blah, blah, blah. -2 equals logarithm, blah, blah, blah. We essentially get 10 to the x. B BH plus. So the neutral base, basic molecule divided by the conjugate acid BH plus is about 0.01 to 1, which is equal to about 1 to 100, right? So yeah, it's not totally the neutral molecule, and we can rely on some of the alternate mechanisms for ionic molecules to be absorbed. Certainly, there's definitely a lot more of the neutral molecule in the ileum environment, right? 1 to 100 versus 1 to about 10 million. There's a big difference. So fluoxetine is absorbed more efficiently in the kind of basic environment of the intestine compared to the acidic environment of the stomach. Okay, yeah, all right. Now, in reality, it's probably, there is probably some stomach absorption, also maybe through paracellular mechanisms. But I think the general rule is that basic molecules are absorbed in the intestine more efficiently, okay? Acidic molecules are more efficiently absorbed in the stomach. All right. Sure. 1 second. All right, we're sharing PowerPoint again, I think. All right. You guys see PowerPoint, right? I can't. 1 sec. I think it is PowerPoint. That's right. All right, cool. So let's move on. Okay, so we talked about acidity, which kind of influences the absorption of drugs. What about aqueous solubility? What about aqueous solubility? Like if a drug is completely insoluble, like it's a grease or something, that won't work. It needs to be able to dissolve into your plasma and be transported to a drug target. So aqueous solubility is kind of a big deal. There's two constants, log P and C log P. They're basically the same thing. C log P is calculated, whereas log P is experimental. What do they mean? What does log P mean? I don't know if you've seen this in your other classes or something. C log P and log P. Yeah, so what is it? How's it determined? So there's kind of like the old way before computers, and now everybody uses kind of computer methods to do this, which is called C log P. So the kind of traditional way is you'd partition your molecule between octanol and water. Remember, most like the alcohols, small molecule alcohols like ethanol, methanol, isopropanol, those actually dissolve in water, right? But octanol has 8 carbons, right? And octanol is just 8 carbons and then an OH. That is actually not water soluble because of the 8 carbons. And anyway, so log P is simply going to be a partition, like an equilibrium constant between octanol and water. That's basically it, right? So it's essentially the concentration of the drug in octanol divided by the concentration of the drug in water, right? And then if we take the logarithm of that, it's just concentration of octanol in water. How would you do that experimentally? Like you could do this. You just go get some octanol, go get some water. I mean, you can even do this on a micro scale. You could use a Eppendorf tube or something, right? You don't need to use a big separatory funnel because that would imply you have a lot of your drug to waste in this experiment. But you could do it like in a Eppendorf tube or small volume thing. And then how would you determine how much of the drug is in one phase versus the other? Kind of becomes a analytical chemistry question, right? Like what technique? maybe you could use HPLC, right, or LCMS or something like that. So you could take a sample of these two and then go analyze them and just kind of figure out the ratio. So it's not that hard, right? If we did a lab course in medicinal chemistry, that's something you might do actually. Okay, so C log, that's log P, all right. For drugs, the range is usually 0 to, which is extremely polar, to about 7, which is very greasy. And by using the logarithm, it helps because it just kind of compresses this value into a very small range. From 0 to 7 is nice, right? So why does solubility and solubility, which is aqueous solubility, right, versus lipophilicity, why does that matter? Any ideas? We know solubility, right? If it doesn't dissolve in your blood, or like physiological solutions, that's not going to work, right? It needs to be somewhat soluble. Why lipophilicity though? Why if a drug is infinitely soluble in aqueous, but not very lipophilic at all, is that going to work? Any ideas? Like perfect solubility. Like think of an amino acid, glycine, phenylalanine. Those are almost infinitely soluble. But what's the problem with a peptide drug? Like, or like if I have a couple amino acids, can I take it orally? We talked about that before. Peptides, right? Highly soluble, but they won't absorb very well, and they won't go through cellular membranes. A peptide will probably be digested in your stomach also. So if you do take a peptide drug, it's probably going to be IV, right? Okay, but then lipophilicity is the opposite of aqueous solubility. It's like kind of greasiness. You need a little bit of greasiness to sneak through cell membranes, right? So basically what this means is there's a window of C log P or log P, a window of log P that works really well. It's kind of like around 3 to 5 or so, 3 to 5 log P. So not too aqueous, not too organic. So drugs need to be dissolved in an aqueous solution, thus they need to be somewhat polar. But they also need to be sufficiently lipophilic, greasy, to pass through bilipid membranes in the intestines and the cell membranes to reach a drug target. So it may have to cross a cell membrane where your drug target is. If your drug target's inside the cell, we need to sneak through that cell membrane also, right? Some drugs need it. Also might need to be even greasier to cross the blood-brain barrier, because if you're treating a neurological condition, that's another membrane, and that's a very greasy membrane. Okay. So C log P, what is C log P? It's simply log P determined by computer program, which is super cool because computer programs are ultra fast. You don't need to go get your separatory funnel. You don't need to waste chemicals. You actually don't even need to use your substance. We just supply chemical structure. We can get a pretty accurate C log P, which is super cool. Okay, so let's talk about these a little more. Any questions yet? Log P, C log P. Have you guys heard of these? Probably, maybe. I don't know. Maybe it's a little more of a med chem concept. I don't know. I don't know if log P is covered in biochem class. Maybe, I don't know. All right. So C log P is convenient compared to log P. Don't need to use a separatory funnel. You don't need to get HPLC, which is $50,000 equipment. The chemicals are cheap though, but it's nice being able to do this in a computer. There are, as you can imagine, is there just one magical way to do C log P? Probably not. There's like 1,000 ways to do C log P. And it kind of depends on what tools you have access to, right? And yeah, fortunately, we have some websites, some web tools that we can do that very basically for free. But there's also really high quality C-log-P programs that cost money that may, if you're making a drug, you want every possible tool at your disposal. So you may pay a company to actually have their C-log-P predictor. We're going to use one called, there's a company called Mole Inspiration, Chemical Informatics. It's a whole bunch of free tools. We like free, especially for a class. So we'll show this Mole Inspiration method in a bit. We'll actually show a couple of these values too. Mole Inspiration, they call their C-log-P algorithm MILOG-P or MILOG-P, MILOG-P. Okay, so it's their little twist on how to calculate C-log-P very efficiently. All right, so what are some C-log-P values of real drugs? Epinephrine, which is adrenaline. The C-log-P is actually small, right? It is a very low number. It's kind of, it's under 0. It's very polar. You can imagine from all the functional groups, the alcohol and the amines and the hydroxy groups. So this can be taken orally, but it's not absorbed super efficiently. And it's mostly used as a neurotransmitter, but it's also absorbed. It's used IV also, but it's got a very low C-log-P or MILOG-P. Aspartame, which is NutraSweet. So this is a peptide, right? Aspartame. I don't know if people even use aspartame as much. Now there's some really nice artificial sweeteners like sucralose and like other things. But this is actually not really, this is not something that we really need to absorb into our body. It's not a drug. It's more of an artificial sweetener. It's 2 amino acids, right? It's what is this one? Aspartame. It's aspartic acid, right? So it's aspartic acid on the left, and then it's a peptide with phenylalanine methyl ester, right? Okay, but yeah, it basically it absorbs into your tongue and then gives you this sweetness sensation. Hydrocodone, which is one of the opioids. So kind of still a kind of smaller C-log-P. It's got a couple polar functional groups like the methyl ether, this other ether, and the amine. And then hydroxychloroquine, which is used as a anti-malarial drug, and it was also kind of one of the early investigated COVID-19 treatments that turned out to be kind of fake drug, I guess. So chloroquine is a very similar molecule. It's got this chloroquinoline structure, but minus the hydroxy group over here. But yeah, this is actually kind of like in the ideal range for a orally available drug. So log-P around 4, sort of middle of the road for log-P. All right. Prednisolone, which is one of the steroidal anti-inflammatory drugs. It's actually, being a steroid, most steroids are actually kind of greasy and a higher log-P, but this one has like 2 alcohols and a carboxylic acid. So this combination of functional groups and also the ketone will really drop the log-P. So this is fairly aqueous soluble. And then we have like maybe a more traditional steroid, estrone, female steroid hormone. It's still a kind of low for being a steroid, and that's due to the alcohol, the phenol, and the ketone. Whereas cholesterol has a very high log-P value because it's very greasy. It's got this greasy tail at the end, and alcohol. The alcohol is actually, probably drops the log-P a tiny bit, but the general greasy nature of the steroid kind of boosts the log-P up. Okay. Yes, is cholesterol taken orally? No, it's not really a drug. but it is a component of our cell membranes. So it fits since it's a lipid bilayer, and it kind of it's one of the components of our cell membranes. That's how it's kind of stored, right? Okay, let's see, polar surface area and TPSA. These are another measure of polarity, and we can calculate it kind of quickly using the computer also. Polar surface area, what does that sound like? Polar surface area. It sounds like if you have a drug, it has a surface, everything's got a surface. It's the amount of polar functional groups and things on the surface. It's kind of correlate or inversely correlates to log P, right? Because if you have a lot of polar functional groups, that'll decrease your log P, but it'll increase your polar surface area. And this is also something that can be calculated kind of quickly. And it's used in drug likeness, so the Lipinski rules and things like that. Okay, or I think actually maybe the Weber rules. All right, so it's another physicochemical parameter. We can calculate it pretty easily, or I think it's almost exclusively calculated. So this is something we use a computer program to determine. I don't think there's an easy experiment like the separatory thermal experiment for polar surface area. Okay, so it estimates the surface area of the molecule that has polar features like polarized functional groups, alcohols, ketones, amines, things like that. Typical number is 0, which is highly nonpolar, to 200 to 300, which is highly polar, lots of polar functional groups. So this kind of inversely relates to the log P, right? Because the log P, the big numbers were kind of greasy, like cholesterol or something. Yeah, complementary and inverse to log P. We can also use a free tool on the Mole Inspiration website. We'll do that later. So it's easily calculatable either through proprietary tools you can purchase or these free tools on the web. TPSA is topological polar surface area is topological polar surface area. It's a very rapid way of determining PSA. It used to be that PSA was kind of a difficult calculation, a very slow calculation. TPSA is a very quick calculation. So what are they computer-wise? So kind of the old way, like you had a drug, the old PSA way, you'd have your drug, you'd turn it into a three-dimensional molecule, three-dimensional shape, and then create a molecular surface of the three-dimensional structure, and then kind of identify the polar atoms and summarize them. It was actually kind of a slow process, right? Dealing with 3D structures is, it's not super slow, but if we have to do this for 100,000 molecules, yeah, it's a little annoying and slow. TPSA does it much quicker, so it's kind of like maybe a more common approach. Basically, and this is a little bit of computer code. The idea is that it's so well understood, polar surface area is so well understood that a computer program can really just look at the different fragments of all the pieces and have a little table. And so it can very quickly figure out the polar surface area of all the little fragments, And then it can just add it up. And it's like 1,000 times faster. And you get a pretty similar number, okay? So 53 versus 51, roughly. I mean, they're pretty ballpark and, similar numbers. Okay, good. Okay, let's get into Lipinski Rule 5 and the Weber rules. We'll do this a little bit, then I'll probably just then continue into the asynchronous lecture a bit. Also, as we, a lot of this stuff is really nice if I do it kind of live for you. So I'll probably record a pretty small asynchronous lecture. And sorry, one sec. A little tickle in my throat. All right, sorry about that. I'm probably going to record a sort of small asynchronous lecture, and then we'll continue with the sort of a tutorial of these, of some of these tools later next week in the next Zoom lecture. All right, but for now, let's talk about Lipinski Rule of 5 and the Weber rules. All right. So these are standard rules of drug likeness that we can use computer tools to figure out, you know, how the potential for a drug to be drug-like, and use it in the screening process if we're doing high throughput drug screening or something. So it would be really ideal to determine this likelihood that it's going to be an orally active drug early in the drug discovery process. I'm going to go cough one more time. I can turn off the microphone. Sorry, guys. It's mute. Give me 1 second. Okay, I'm back. All right. So yeah, it'd be nice to do this process and can kind of figure out oral drug availability early in the drug screening process and try to, you know, change any problems with the drug structure earlier rather than later. And there's a couple of ways to do it. One's the Lipinski method, and the other's the Weber method. And it'd be great if we can do it using very simple numbers like C log P, TPSA. We can calculate these very easily with tools and do it on hundreds of thousands of molecules very rapidly using, yeah, websites or a computer program or something. And there's a couple of these methods. Lipinski and the Weber are among several. There's not just two, there's probably like 5 or so. Rule of 5 though is like kind of one of the first ones that's still used a lot today. The Weber one, Weber rules of drug likeness, it's maybe the rule of 2 because there's only 2 criteria to worry about. Works well also. Sometimes people use both rules just to kind of triage a molecule to see, like, is it likely to, I mean, if it obeys both rules, that's probably a good sign that it might be a good drug. A couple of the references, Lipinski, 2001, Weber, 2002. Lipinski was at a big drug company, maybe even Pfizer. I can't remember it the second, but he was a hardcore, big-time medicinal chemist. Weber, I think, might be academic. I can't remember, but these are classic papers in medicinal chemistry on these drug-like criteria. The Wikipedia page on Lipinski Rule of 5 is actually really good too. It's a pretty nice, simple overview of the different rules. Okay, what are the rules? The Rule of 5. So there's no more than 5 hydrogen bond donors. No more than 5 hydrogen bond donors. Okay, so those are things like OHs and NHs, right? No more than 10 hydrogen bond acceptors. Those are things that can accept a hydrogen bond, like an oxygen or a nitrogen that may not have a proton on it, but it's got a lone pair that can go grab a proton. Molecular mass, less than 500. Okay, so we can see this rule of 5. It's like things that are kind of related to 5. So molecular mass has to be less than 500 for Lipinski to be obeyed. The octanol water partition coefficient, that could be log P or C log P or MI log P if we're using the molecular inspiration website, should be less than or equal to 5. That's another rule. And the rule states that one violation is allowed. So you can violate one of these rules and still be okay and then Lipinski compliant. Okay. With the Weber rules, there's only 2 rules, and that makes it easier. 10 or fewer rotatable bonds. So, and we'll look at examples of this. It's usually pretty easy to figure out what a rotatable bond is. It's usually atoms that are not in rings that are kind of like poking out that can rotate around. We'll look at those in a second. And the Weber second rule is the PSA or TPSA, because that's what you got, cannot be greater than 140. So that's nice. This is a pretty simple set of rules. And there's no exceptions to the Weber, whereas with Lipinski, you can have one violation. And both rules have exceptions. They're not perfect, but are regarded as good guidelines for preclinical drug discovery. So often, if you look at a paper, and maybe even some of the papers we've looked at in our homework, they'll talk about Lipinski compliance and maybe even Weber compliance also. Okay. The Wikipedia page is pretty good. All right. Okay, let's show a couple examples. Okay, so those are the rules. Lipinski allows one violation. The Weber, no violations are allowed. So let's look at this molecule. What is this molecule? This was doxorubicin. So it's a pretty big molecule. What are the violations? Any violations? So for Lipinski, there's 7 hydrogen bond donors. The molecular weight's 543. C log P is negative 1.7. Is that big or small? It's, you know, it's pretty tiny, remembering that usually the range is about 0 to 7 for most molecules. And hydrogen bond acceptors are 12. Okay, so what do we think here? What do we think? Hydrogen bond donors should be less than or equal than 5. Okay, that looks like a violation, right? Molecular weight should be less than 500. Okay, that looks like a violation. C log P should be less than or equal to 5. Well, that's not really a violation. It's small, but it's not a violation. Hydrogen bond acceptors is equal to 12. So that looks like a violation. So we got a couple violations here. The Weber rules, there's 11 rotatable bonds, so it looks like a violation. Polar surface area is 206, so that looks like a violation. It also, we're listing the hydrogen bond. I don't know what that is actually. Hydrogen bond. I think it's donors plus acceptors. I don't know why it's listed there. Okay. Anyway, so this kind of shows what the an analysis of these rules. And oh, look at this. The oral bioavailability is approximately 5%. Oh, wow. Okay, well, that makes sense now because it's actually in violation of the Lipinski and the Weber rules. Everything's exceeded except C log P, right? So hydrogen bond donors and the molecular weight are in violation. C log P is considered okay, according to Lipinski. Donors are 12. And rotatable bonds 11, PSA equals 206. So this actually showed, this kind of validates the Lipinski and the Weber rules a little bit for a kind of extreme molecule. And doxorubicin is a useful anti-cancer drug, but it's usually injected IV, right? Okay, pretty cool example. Yeah, all the guidelines are exceeded. Okay, let's look at rotatable bonds and see. Because they're seeing 11, I'm seeing around 12. What do we mean by rotatable bonds and how do we calculate them? Okay, so what is rotatable? Definitely not none of the ring stuff, right? However, like the OH, I consider rotatable because that can rotate around and the proton can be in different places. So I consider that's gonna be one. Also the OCH3, and also the bond between the oxygen and the carbon. I think that's rotatable, and also this one. So I see right here, I see 1, 2, 3, and 4. Okay, so 4 on the left. And then up here, that's definitely a rotatable bond because that bond can rotate, right? 5, 6, 7, and 8, 9 because the OH can rotate around, 10. That bond's a rotatable. 11. I think I said 12. I'm actually seeing about 14 now. I think that's rotatable, and that's rotatable. So I don't know. It's a little hard, and I had to actually look up a good definition of this. Let me try this again. I said 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, actually, let me see what the definition said again. It's underneath. Okay, this is from the Weber paper. Rotatable bonds were defined as any single bond, not in a ring, bound to a non-terminal heavy atom that's not hydrogen. Okay, so these OH, the carbon to oxygen is rotatable, but the oxygen to the proton's not. That's what I screwed up. It's a heavy non-hydrogen atom. Okay, so we'll try to do this again. Excluded from the count were amide CN bonds. We don't see any amide CNs here anyway. Let's try this again. Okay, so I see that one. That's 1, 2, 3. So those right from the oxygen, carbon to oxygen and oxygen to carbon. Those count. So 1, 2, 3, 4, 5 from carbon to oxygen, 6 from carbon to carbon, 7 carbon to carbon, 8 from carbon to oxygen. So we have 8 now. 9, 10, 11, and 12. And I think this might be another one. From carbon to carbon, that is a rotatable bond. So I'm actually counting about 13 now. So, but anyway, nevertheless, the bottom line is it's more than 10. So it's definitely a violation. The exact count, I'm seeing about 13, but okay, in violation. All right. Okay, let's do another one. Okay, so this is a neuropeptide Y1 antagonist. It was a drug discovery project. Let's look at this molecule first. The potency is about 2 micromolar, which is not super potent, right? Not super potent. You'd rather it be nanomolar, right? But micromolar, if that's what you got, that's what you got. Okay, so is it Lipinski compliant or is it Weber compliant? Hydrogen bond donors is 0. Is that good or bad? Donors are 0. Well, less than 5. Good. Hydrogen bond acceptors is 3. And do we see any donors? Hydrogen bond donors. Do you believe it's 0? Do you see any? It should be 0. It is 0, but you understand what a hydrogen bond donor is, right? It's like an OH or an H. Hydrogen bond acceptors 3, right? So we see 1, 2, and 3. Is the nitrogen, the oxygen, the 2 nitrogens and the oxygen is 3, right? Is that in compliance? Those are acceptors. Yeah, that's in compliance. Molecular weight. is 369. Yeah, that looks pretty compliant. Log P is 5.7. Okay, so a little bit outside of Lipinski. Polar surface area is for the Weber rules, and yeah, that looks compliant. Rotatable bonds is 6 and versus 10. Let's see if we can get 6. So I see that's a rotatable bond, and that's a rotatable bond. That's 2. Those are totally rotatable, right? They can rotate. 1, 2. That's a rotatable bond. That's 3, 4, 5, and 6. I might call that a 7th one, but nevertheless, there's a little bit of I don't know, ambiguity, I think, under rotatable bonds. Let me see if I get 7 again. 1, 2, 3, 4, 5, 6, 7. I kind of think there's 7 there. But nevertheless, it looks like it is 7. Yeah, rotatable. I think it's 7. The potency is kind of bad, but these things are Lipinski compliant. That's nice. Log P is out of Lipinski. Polar surface area, rotatable bonds. Okay, well, that's not that bad, right? Is this overall Lipinski compliant? Yes or no? Of course, 1 violation is allowed. So yeah, Lipinski would say that this is an okay molecule, right? Okay. Now, what they did in this paper is they played around with the structure, right? Why do you think they played around with the structure? Because it wasn't very potent. So they're like, okay, let's optimize it. Let's play around with it, change the structure around, see if we can enhance the potency, right? It's a drug discovery paper. So let's do that. So that's what they did. So now they came up with a molecule. It's got an extra 6-member ring up top. This part's the same with the chlorophenyl ether, yeah. And then instead of the methyl group, they added a couple carbons and another 6-member ring. Sweet. What happened to the potency? Oh my God, it's nanomolar now, right? It's 1 nanomolar, so massive boost in potency, right? But it's poorly orally absorbed, which can be probably predicted by the Lipinski rules. So let's do the Lipinski analysis. Okay, so hydrogen bond donors now is 1, right? You see it? Where's the hydrogen bond donor? You see it? It's the NH, right? Is that in compliance? Yes, that's in compliance. It's 5. You know, 1 is less than 5. Hydrogen bond acceptors, now there's actually 6. So that is also in compliance. Hydrogen bond acceptors is still in compliance. You see 6? 1, 2, 3, 4, 5, 6. Good. Hydrogen bond molecular weight is now not in compliance. It's 591. Okay, so that's a violation. Log P is now 7.3, so that's in violation too. Polar surface area is 50, so that is in compliance, but the rotatable bond count they're saying is 14 now, which is not in compliance. So this is totally, you know, this kind of fails the Lipinski test and the Weber test. Let's see if I can match their 14, because I have a little difficulty with that. So let's see. What are rotatable up here? I see 1 right there. Yeah, that's 1. I see 2. Yeah, that's rotatable bond. Yeah. I see that one. That's rotatable bond. That's 3. So 1, 2, 3. That's rotatable. That's 4. 5, 6, 7, 8. So it's at 8 now. 9. That's rotatable. 10, 11, and 12. And I think, yeah, I don't know where they're getting 14 from. I'm just seeing it a little differently. And I think I said that down in my notes here. Yeah, 12. I don't know. I think I disagree with them. But nevertheless, 14, 12, you know, it's still it's not really even close. It's definitely outside of the Weber criteria. Okay, so yeah, good potency, good oral drug absorption. Got some good Lipinski parameters. We have 2 bad parameters, so that makes it in violation of Lipinski. Polar surface area is good, but the rotatable bond count is bad. So based on all of this, you'd say, okay, if it fails Lipinski and it fails the Weber. Okay. All right. I think I'm done. We're out of time. Let me just see what the next topic is. Yeah. So what we're doing next, and I'll do a little bit of this. I'm gonna do a short lecture, asynchronous, because I kind of want to demonstrate some of the tools when we're all Zooming, and so you guys can ask questions in real time. But I'll talk about a little bit of the SMILES stuff and the 2D and 3D structure generation. So I'll probably do like a shorter than normal asynchronous lecture. All right. Have you guys seen any of this stuff before? Or I'm trying to figure out, is you guys learn this stuff anywhere? I don't know. Lipinski, and I mean, it's kind of a sort of a drug thing. And I guess if you haven't had a medicinal chemistry course, I don't even think you learn this in a pharmacology, the kind of pharmacology course like in the biology department. You probably won't learn a lot of this stuff. So a couple of people are saying no. So I think it's interesting and it's cool. It's very doable, especially if you're using computer programs to do all the hard work. I love using computers to do hard work. All right, are we good? I think we're good. Any parting questions, thoughts, concerns? I'll maybe try to have a new homework maybe on Friday. We may have to wait another week so you guys are more proficient with these tools. But yeah, and anyway, we'll have homework here pretty soon. All right. We're good? All right, we're gonna stop the sharing, and I'm gonna stop the recording.